there is inside the machine, between the stator, means this entire part, and between the rotor, rotating part, there is an air gap. So as the pole spreads, automatically the air gap will be reduced. I have told you what is the significance of air gap in a simple diagram. As the air gap increases, the MMF requirement automatically increases. And I want to tell you one thing here only. In the rotating part, EMF is induced. Means mechanical to electrical energy conversion is happening in the rotating part. If you take this as an armature, next part is armature, that's what it is. So let us take this is the armature. You are giving mechanical input to which part? Armature only. You are rotating the armature, right? You are rotating the armature, which you are giving mechanical input to the armature, and where you are getting the induced EMF, where you are getting output? Armature only. So armature is the main part in the machine, is the heart of the machine, where mechanical to electrical energy conversion is taking place. Let us consider this machine acting as a motor. When it is acting as a motor, you will apply voltage. You will apply voltage across armature again. Means you are applying electrical input across the armature, and automatically the armature starts rotating. So you will collect the mechanical output again from the armature. So the rotating part is the main heart of the DC machine, whether it is acting as a generator or a motor. You are giving mechanical input, collecting electrical output. You are giving electrical input, collecting mechanical output entirely through the armature. Keep the heading, armature.
You get the white चढ़ा है
पहले भी कंपनी की मार्केटिंग बताया दुकान का मैल का टैग ओए दुकान का मैल का टैग तुम ले आओ रोड को पे बना लो
Electromechanical energy conversion. Right now, electromechanical energy conversion. Electromechanical energy conversion happens in the rotating part of a DC machine. In the rotating part of a DC machine. Which is nothing but armature core. Which is nothing but armature core. Energy conversion occurs. Energy conversion occurs through a coupling medium. Energy conversion occurs through a coupling medium, that is magnetic field. Through a coupling medium, that is magnetic field. Listen, once listen. Energy conversion from mechanical to electrical or electrical to mechanical. This conversion is happening in the armature core. When there is flux, when the conductor cuts the flux, EMF is induced in that. So, similarly, when there is flux, main flux, and there is armature flux, they are interacting each other, and the armature is subjected to a force. So, it rotates. Finally, what I want to convey here is, between this energy conversion process, anything to anything, inside there is a coupling medium that is nothing but magnetic field flux. What I want to tell here is, when flux flows, it won't produce temperature rise. When current flows, it produces temperature rise. Just understand this relation. Previously, we have discussed one thing. There is a current carrying conductor, some resistance you have offered, you have applied voltage V, this is I. When current flows, will the conductor get heated up or not? Did you touch a magnet from for example, toys or something? Did you see permanent magnet? Did you touch, if you touch that magnet, will it be heat state? How much time if you operate the magnet won't get heated up, right? Means the flux, when it is flowing, there is no temperature rise. Can we say that or not? Now, energy cannot be created nor destroyed. It is changing from one form to the other. Temperature rise, temperature is one form of energy. It can't be created. It is converted from given input. Means if you are giving some input, this input, you are getting some output. This input is not exactly output. You can take this as plus some heat. Without the heating of the machine, you won't get anything. Yes or no? It may be any loss. It may be copper loss, it may be Eddy current loss, it may be hysteresis, it may be mechanical, it may be frictional, any loss. Final format is temperature rise. Energy cannot be created nor destroyed. This temperature rise is some part of energy lost out of input. Is that clear? Now, when flux flows, there is no temperature rise. Means magnetic medium, through coupling magnetic medium, is lossless or not? Can we say that or not? If current flows in a conductor, current and flux both are synonymous, right? Parallelism. If current flows in a conductor, the resistance is producing temperature rise, but the reluctance is not producing temperature rise. Means what? The magnetic medium is not loss. Means temperature rise is not there. Means if temperature is not there, means automatically losses are not there. So magnetic medium is better than electric medium. Remember this. And you know basics like permittivity and permeability. Mu is equal to 4.10⁻⁷ permittivity. Based on that also, if you prefer magnetic medium as a coupling medium, if you ask in interviews, I'm telling these things, in interviews you will be asked why magnetic medium chosen means. Particularly electric medium has losses. When I simply explain like this, when current flows in a conductor, the conductor gets heated up. Some part of energy is converted into heat, which is lost. When flux flows in the medium doesn't get heated up. No heat produced means no loss there. Is it right? So like that, there are many advantages of this coupling medium. Now if you observe, there is flux between stator and armature. And this flux is interacting with the armature and is produced. So the coupling medium is entirely the flux here. So when flux wants to pass through the armature should make the flux should flow freely into it. Yes or no? The flux should flow through the armature freely. Means the armature core material should contain superior magnetic properties. You have written under yoke good magnetic material, but under armature core you have to write superior magnetic material. Why? Because all the work has been done in the armature only. But yoke, it is just to make flux of 5/2 to flow through it. So when compared to yoke, the armature core should contain superior magnetic properties, that is high permeability. Right? The core material should be a superior magnetic material. Superior magnetic material. With high permeability. High permeability. Just for understanding, I have written like this. Permeability, ability to permit flux. generally, steel is used. Steel is used. But steel has high conductivity. Steel has high conductivity to eddy currents. Conductivity to eddy currents. Therefore, cores are laminated. Cores are laminated and alloyed with silicon. And alloyed means mixed with silicon. Around 3.5 to 4% only. (3.5 to 4% only). Listen, this is the material. Once listen now. Let us take armature core as a solid cylindrical drum. What is the purpose of armature? Basically, to hold the armature conductors. So it is slotted now. It is slotted. So in these slots, what are placed? Armature conductors are placed. So the armature is mounted on a shaft. Means inside there is a shaft coming out. So you will connect a motor and you will rotate the armature. So when you rotate the armature conductors on the armature peripheral will cut the flux. At the same time, armature core also cut the flux. Yes or no? Definitely armature core, which is a good conducting material, high permeability, will also cut the flux. When it cuts the flux, what is produced inside? EMF. According to Faraday's law, whenever a conductor cuts flux, EMF is induced. So in the armature core, EMF is induced. If EMF is induced, automatically it's a closed structure. So what are produced in it? Currents. So these currents are unwanted currents actually. The currents which are flowing in the solid core cross-sectional area will simply circulate themselves. They circulate continuously within the core and produce again temperature rise. Temperature rise means some part of electrical input, some part of energy is wasted as loss. So this temperature rise is most important not because of reducing the efficiency. The problem is the rise in temperature will destroy the machine. Losses are important not because of the reduced efficiency. There are many factors why losses are important, but in the top priority you have to give to temperature rise. Why? Because if losses are more, output is less, efficiency is less, you require more input. All these things are different. If losses are more, the rise in temperature is more, and you can't operate the machine more than 1 or 2 hours because the rise in temperature is proportional to time of operation. As you keep on operating, at the end of the day, finally the temperature rise will destroy the machine. So you have to design the machine to be as minimum loss as possible because of the temperature rise. So as these circulating currents, which are known as eddy currents, which have no definite direction or destination, simply circulate within themselves, you want to reduce those eddy currents, so don't prefer solid cores. You have to laminate the core. Means if you take a simple cylindrical drum, because of the large cross-sectional area, as you know, the resistance is equal to rho L by A. As the cross-sectional area increase, automatically resistance will decrease. Resistance is reducing means conductivity is more. So conductivity to eddy currents are more. For example, if you go on a road, the road is very wide, empty, how will you move without any direction? You will encourage it to move like this. Similar manner, cross-sectional area wide means there will be large eddy currents. So the idea of lamination is, instead of going for a solid cylindrical drum like that, you go for thin sheets like this. let us say, if this solid drum is cut into 10 or 20 pieces, each one having 1 mm thickness, imagine, each one is having 1 mm thickness, it is cut into 10 pieces like this, and each lamination is dipped in varnish coating, some paint or varnish or some enamel coating, you dip in that, or you maintain some paper between one lamination and the other lamination. Means what you are doing, you are electrically isolating each lamination. You maintain thin coating on either side of the lamination and stack them together. That is known as laminated core. What you are doing means, without reducing the cross-sectional area, you are making the solid core to act as, you can think like this, each lamination act as individual core to form single core. Can we say that? Each lamination is now one core. This is one core, this is the other core, this is the one more core. So like that you have 10 cores which are joined together to form one core. This is one core having a thickness A, for example. This is also one core, but individually having some A by 10 thickness, let us say. So this is also forming one core. The difference between that and this is, if you see eddy currents, here also eddy currents flow, but where are the eddy currents? They will flow only in each lamination, because between each lamination what is produced? Thin insulation is there. So by electrically isolating, the flux will link, flux will pass through the core, no problem. But these eddy currents will not circulate as freely they were circulating here, and finally you are reducing the eddy currents. In any meter or anywhere, if you see laminations or strands or anything, if you see laminations, it is to reduce eddy currents. What are you doing by lamination means, you are making thin sheets of 0.4 to 1 mm between that. This is the thickness, 0.4 mm to 1 mm. The minimum thickness you can go beyond is only 0.35 mm, because lesser the thickness, what happens, the mechanical strength of each sheet will be less. So you can't go beyond 0.35. So this is the thing. Now, these laminations are stacked. Each lamination acts as individual core to form one single core, and the eddy currents in each lamination will not flow easily. So what you are doing, you are reducing the eddy currents. Next point is silicon. Why you are adding silicon to steel means, steel has high conductivity to eddy currents. One thing, you have to reduce the conductivity of steel without destroying its magnetic properties. That's the aim now. You have to reduce conductivity, means the ability to permit currents. You take like that. Conductivity means ability to permit current. Permeability means ability to permit flux. Both goes in the same line, but you have to reduce conductivity but not destroying permeability. That can be done by adding silicon. Silicon material has that characteristic. By adding silicon to steel, which is also called as electrotechnic steel, or electrical steel, so by adding silicon to steel, what it is doing means, it is not destroying magnetic properties, but it is reducing conductivity to eddy currents. As well as in losses topic, we will discuss this thing. Hysteresis loss formula is there. In that formula, it's like this: hysteresis loss is equal to some constant kh into V max whole power 1.6 FV. V is the volume. We will have formula. We will discuss later in the losses topic. What I want to convey is, there is 1.6 here. 1.6. This is actually X. It is the range between 1.5 to 2.5. Depends on the material you are using. since we are using silicon steel, silicon is generally preferred in all the core preparations. Silicon has a value 1.6 hysteresis coefficient. That's why you are keeping 1.6. So using silicon to steel will reduce eddy currents as well as hysteresis loss. We'll discuss the losses topic right at this point. This should be X. That depends on the material you are using. By adding silicon to steel, the conductivity reduces without disturbing magnetic properties. Silicon also has low hysteresis coefficient. 1.6. Consequently, produce less hysteresis loss. Armature core. Next point. Armature core is made up of thin sheets of silicon steel. 0.4 to 1 mm thickness. 0.4 to 1 mm thickness. With a layer of insulation on either side. Each lamination act as individual core. To form single core. So generally we will be studying all the cores are made up of silicon, steel, laminations. So laminations are to reduce eddy currents. Adding silicon to steel reduces eddy currents as well as hysteresis loss. The purpose of armature core. The purpose of armature core is to hold conductors is to hold conductors in bracket winding. Conductors in bracket winding, which is punched into slots. Which is punched into slots on the outer peripheral. On the outer peripheral means surface, skin, outer peripheral. It is mounted on a shaft. It is mounted on a shaft. Generally, this is known as keyed to the shaft. It's like a key inserted inside. So we'll discuss more things regarding Eddy current laws, regarding hysteresis laws in the laws topic, not here. So the next one is armature winding. So armature winding we discuss at the last because this is a big topic, important one. Let us complete the remaining things. After armature winding, the next one is at the end of the armature, what is connected? Commutator. Keep the heading commutator. So previously we have taken one turn or a coil like this and we have drawn insulation segments A, B. Don't draw this, just for a reference. Actual commutator in the machine, how it will be means, for our understanding we have taken one coil or a turn like this rotating between north and south poles. This is what the discussion is. But practically, there is no one coil. There are many coils arranged in series. Armature winding, I have made it to conductors in bracket winding. Conductors are made into turns, turns made into multi-turns, multi-turns made into coils, which are arranged in series, uniformly distributed on the armature peripheral. That's the basic definition of armature winding. We'll discuss that. But before that, if you see this is one coil connected to two segments, for example, if there is one more coil, like that there are some n number of coils which all should be connected in series through commutator segments means you will have many segments on the commutator surface. So practically how the commutator will look like means there are many splits inside with mica insulation, 0.8 mm thickness. These are the splits made through mica insulation segmented. So this is 0.8 mm thickness mica insulation, this line. You take like that. Between insulation and insulation there is segment, one segment will be there. So previously I have given a side view for your understanding. So at the end what is there? On the shaft there is a commutator, right? So this is the diagram I am drawing. The commutator represents like this. So let us take, there is one coil inside. Listen carefully, once listen. One coil, two segments. One coil, two segments. Now, there is one more coil and both coils are in series. Think like that. There is one more coil on the armature, both are in series. Why you have to connect in series means, let us say, here three conductors are in series. I am representing the resistance as one conductor. Let us say in this there is 1 volt. In this conductor, by cutting off flux, let there be 1 volt induced EMF. In this conductor, 1 volt induced EMF. In this conductor, 1 volt induced EMF. What is the voltage across these 3 conductors in series? 3 volts. This is 1 volt, 1 volt, 1 volt. Total is 3 volts. If you connect all these 3 in parallel, what is the voltage? What is the voltage? 1 volt. So, armature winding is all the conductors are in series. Now, I want conductor should be connected in series through commutator. So, let us say there is one more terminators. How to connect in series? If it is connected here, are they in series or not? Observe the diagram. Series or not? Next. There is one more coil. Again, I want this in series. Again, this should be connected here. This is here. Right? So, like that, all the coils are connected in series through the commutator. Now, observe carefully. 2 conductors. This one, let us say one side of a coil. Let us say this is one coil. This is one coil side. This is one coil side. 2 coil sides are connected to one segment. 2 coil sides are connected to one segment. 2 coil sides make one coil. Observe these 2. 2 coil sides are making one coil. If you say this is a coil, this is a coil, this is one coil side of a coil, this is one side of a coil known as coil side. So 2 coil sides are making one coil. 2 coil sides are connected to one commutator segment. If there are 10 coils, how many commutator segments you will have? Simple. Is it clear? If you have 10 coils in the machine, you will have 10 segments. If you have Z number of conductors, if you say Z by 2 are the coils, how many segments you will have? Z by 2. That depends on the question. Is it clear? So number of commutator segments are always equal to number of coils. Commutator is nothing but the image of the winding inside. Commutator is nothing but the image, reflection of the winding inside. Anything happens on the commutator directly affect coils inside. Yes or no? Anything happens on the commutator. For example, let us say there is a short circuit. There is a short circuit. For example, think why short circuit comes, we'll discuss. Let there be short circuit. If anything happens on the commutator, because why I am telling commutator is outside the machine, yes or no? Commutator is not inside, commutator is outside, where you are collecting output. So this commutator, anything happens, if 2 segments are short circuited outside, immediately inside the armature, 2 coils are short circuited. So commutator plays a vital role in collecting the current, no doubt. Anything happens on the commutator directly reflects onto the winding. So while collecting current from the commutator, it should be as sparkless as possible. It should be as sparkless as possible. We'll discuss respect to these points. Commutator is a split ring. Commutator is a split ring which is also mounted on the shaft. Which is also mounted on the shaft. Rotating with the coil. Rotating with the coil. It is made up of hard drawn copper segments. Hard drawn copper segments with 0.8 mm thickness mica. With 0.8 mm thickness mica insulation. Armature coils. Armature coils are connected in series. Are connected in series through commutator. Are connected in series through commutator. Number of commutator segments are equal to number of coils. Number of commutator segments are equal to number of coils. It is the image of winding inside. It is the image of winding inside. Now listen. This is the commutator practically. This is the shaft. Inside there will be shaft coming out. It is rotating continuously. Coils are inside the armature. Now you will connect two brushes to collect current. So when you connect two brushes like this, which are stationary, and if you want to connect the load now, when you connect the load, automatically current flows. Yes or no? For example, let us represent some resistance across a load. Let us take a small battery. If you have a battery, 1.5 volts battery, plus minus readily available, like this, there is plus and minus readily available inside voltage. It is rotating. Now what we can connect? We can connect some, let us say you have connected some bulb across these two brushes. Immediately what happens? Current flows, right? Immediately through the load, current flows. Current is flowing through the armature coils as well as brush and through the load. This is the closed part. Through the armature coils, through the brush, through the load, the current is flowing like this. When you connect some load, as the current flows, similar to that. When the brush collects current from the commutator due to load, when the brush collects current, commutator is continuously rotating. Brushes are just stationary sliding contacts. As it is continuously rotating, the peripheral velocity is very, very high. Peripheral velocity means number of commutator segments per second. You can take like this. Let the machine is running at 1000 rpm or 1500 rpm. This is the speed of rotation, revolutions per minute. We are interested in the number of segments passed by a brush in 1 second, like that. So the peripheral velocity is very, very high. So you can expect some 5 or 10 commutator segments passed by a brush in 1 second. Now, if there exists any improper connection between the brush and the commutator, it may be electrical, it may be mechanical. Any improper electrical or mechanical characteristic, it will give rise to sparking. What is a spark basically? Spark you can take, you can understand like this. Current flowing through air. Can current flow through air? Air is a natural insulator. Between two overhead lines, is there any insulation outside? No. Air itself acts as a natural insulator. But when the potential increases, automatically it will conduct the air through spark and the current will enter. Sparking means you can take like current flowing through air. Now, if there exists a small air gap between the commutator and brush, what happens? A thin air gap, if it exists, definitely the current flows, the brushes are collecting current, so the collection of current will be happen through a spark, definitely. Now, when 10 segments pass by a brush in 1 second, definitely there is a chance of spark spreading onto 5 or 6 segments, yes or no? When a spark spreads onto some 3 or 4 segments, it is nothing but a short circuit inside the coils, yes or no? Spark means it's a conducting ring, you can take like that, a conductor placed like this. So, if there is a conductor like this, automatically inside the coils corresponding to the segments will be short circuited. So, short circuited means it's like high current. Whenever there is a short circuit, automatically it produces a high current in the short circuit. So, what happens in the coils inside? They will get damaged. So, the collection of current from the commutator through brush should be as sparkless as possible. For that, you need to offer good mechanical conditions, good electrical conditions. Discuss. Keep the heading brushes. Brushes are stationary sliding contacts. Brushes are stationary sliding contacts placed on the commutator. Placed on the commutator. Through brush holders. Through brush holders. And a spring. And a spring. They offer electrical connection between. They offer electrical connection between stationary load and rotating commutator. Stationary load and rotating commutator. Change the color and write on this point. The collection of current. The collection of current should be as sparkless as possible. Should be as sparkless as possible, which is known as successful commutation. Which is known as successful commutation. Listen, if you are given any question or an interview, if you are asked like this, the speed of a DC machine, the loading of a DC machine, the current of a DC machine means load current of a DC machine is governed by the following factors. You are given A, B, C, D options. In those options, if you see commutation, opt it. Is the point clear? If you are given any a question about DC machine like this, the loading on the DC machine is governed by, is affected by, the current rating of the DC machine is affected by, the speed of the DC machine is affected by. Like that, if you are given the operating constraint of a DC machine is affected by. In the options, if you see commutation, you opt commutation. commutation plays such an important role in the operation of a DC machine. Why? Because even though you design DC machine to be successful, excellent electrical characteristics, everything is proper, finally, if the brushes collect current with a spark, the machine is of no use, because due to high peripheral speed, if the spark spreads on 3, 4, 5 commutator segments, the winding inside, the coils inside gets short circuited, and it will provide a huge current. Huge current flows in the coils inside, and automatically they will burn. Therefore, commutation plays a vital role. What is successful commutation means? If a brush collects current without sparking, successful. If a brush collects current with some spark, it is not successful. We'll discuss more things under commutation topic later. But here, the basics are, the brushes need to collect current without any sparking. For that, you require two main things. The machine electrical design should be perfect, mechanical design should be perfect. Right on. In order to achieve successful commutation, the mechanical conditions as well as electrical conditions of the brush should be perfect. Now, as you know, mechanical conditions, it's very simple. If the brushes are tightly held on the commutator, definitely there is a friction, there is a temperature rise, and there is a chance of sparking. If the brushes are loosely held on the commutator, definitely there will be an air gap. Since you can't expect a smooth commutator surface, it will be smooth only, but definitely a small fine variations will be there. So the brushes are placed on the commutator with a spring. You know, spring offers some flexibility, tension. So automatically, by adjusting the spring tension, you can make the brushes to be rest on the commutator with proper mechanical conditions. That is one thing. But second one is, I made you to change the color of the pen right on the statement. MNA, did you remember? Magnetic neutral axis to connect here, right on. Brushes are always placed on MNA. For the commutation to be successful. Now listen. You can place brush anywhere on the commutator to collect current. You can place anywhere. Let us say this is the armature. So you have two holes. Outside there is a commutator segment representing this armature. You can place the brushes in this MNA zone, or you can place the brushes in polar axis, where EMF is maximum, this zone, wherever you can place, or you can place brushes here also. Anyway, at 2 points, one positive, one negative, you have to tap the armature. That is what the aim is. There is an armature, you are getting voltage. So anywhere at this point or at this point, you have to collect the voltage. So you have one neutral zone. This is the neutral zone, and where this is the EMF is maximum. Inside, the armature conductors are in series. Don't divide them. Don't think that the EMF induced in this coil is 0. So when you keep the brush across the brushes, the voltage is 0. Don't think like that. Is the point clear? One brush is placed here, one plus is placed here. Across this you are connecting the load. Since the EMF induced in this coil is 0, in this coil is 0, don't think that the voltage across the brushes is 0, because inside there are many coils in which connection? Series or parallel? Series. So what is the total voltage across these two? 1 plus 1 plus 1 plus 1. You have to add, right? If you have 10 conductors in series, each conductor is cutting the flux, and in each conductor 1 volt is induced. What is the total voltage? 10 volts. Like that, what is the voltage across these two? 10 volts. Don't think the voltage is 0. Don't divide them. Don't isolate them. Those two coils all are in series. Now, let us consider these are all the conductors in series. So, you can place these two brushes in this location, or in this location, or in this location. When you collect the current in the neutral zone, current is flowing like this. Current is flowing like this. When you collect the current in the neutral zone, that is best not to get any spark. That's the best condition, not to get any spark. Why spark comes? Because of the electrical conditions. If you have high voltage here, it will always encourage sparking. So if you collect the current in this zone particularly, what happens? Maximum voltage, high spark. Even if you collect current, definitely here, high spark. So in this entire armature, you require 2 points to collect current. Any point. Which is the best condition, best axis to collect current from the armature? Is it MNA or not? Neutral zone. In order to achieve the collection of current without any sparking in a DC machine, always brushes need to be placed on MNA. If MNA shifts, think like that. MNA is not a physical axis, not a pole. Let us think imaginary axis. If MNA is not here, MNA is shifted due to some reason. What is the reason? We'll discuss. Due to some reason, if MNA shifts, what we have to do for improving commutation? Shift the brushes also. Is the point clear? For some reason, if MNA shifts, then if you want to improve commutation, brushes also need to be shifted onto MNA. The brush materials used are, right on. The brush materials used are copper, carbon, and electrographite. Copper, carbon, and electrographite. Generally, carbon brushes are preferred. Generally, carbon brushes are preferred. As they improve commutation. Carbon brushes are preferred as they improve commutation. So there is a topic known as commutation immediately after armature reaction concept. Then you will understand how a carbon brush will improve commutation. Then we will discuss more things regarding the brush materials. There you will write something regarding that. Just make a note, refer commutation. We will discuss more on this topic under commutation heading. So how carbon brushes will improve the commutation, understand clearly under this topic. shaft and bearings. So what is the purpose of a shaft? So as you know, the armature core is mounted key to the shaft. So when the machine is acting as a generator, mechanical input is given across the shaft. When the same machine is acting as a motor, mechanical output is collected across the shaft. So finally, to give mechanical input or to collect mechanical output, we are using shaft. The armature is mounted or keyed to the shaft to collect or to give mechanical input. And bearings are which will offer the rotation, because the yoke is a stationary part. You have to make the armature inside, which is rotating one. So through bearings you will connect it. Right. The armature is keyed to the shaft. The armature is keyed to the shaft. Which is held by the stator. Which is held by the stator through bearings. Through bearings. To give mechanical input or to collect. To give mechanical input or to collect. The mechanical output. So now the important part is armature winding. Listen. According to definition, armature winding is conductor made into turn, which is further made into multi-turn. These multi-turns are known as coils. Such coils, there will be many in number, all are connected in series through the commutator. At the end, I will make you to solve one problem. You will understand clearly what is happening inside the machine. What is the voltage in one conductor? What is the voltage induced in a turn? What is the voltage induced in a multi-turn in one coil? Output across the brushes. Everything you will clearly understand that problem. This is one conductor. One conductor. This is the other conductor. So two conductors are connected at this end like this. This is one, and at the front end also they are connected like this. So this is one turn. If you have two turns, again one more turn. Like that, there are multi-turns. According to the basic definition of armature winding, all are connected in series, uniformly distributed. What is the purpose of armature first of all? What is the purpose of this winding? For example, if one conductor voltage induced is 1 volt, let us say. In this conductor, voltage induced is 1 volt. What is the total voltage of a turn? 2 volts. So one turn has 2 volts. Let us say one turn has 2 volts. If it is a multi-turn, if there are 2 turns, how many volts you will have? 4 volts. If you have 3 turns, how many? 6 volts. So this is a 3-turn coil. Can we say that? This is a 3-turn coil. This is single turn coil. What is the difference between a single turn coil and a 3-turn or 4-turn coil? Voltage is getting multiplied, right? Voltage is getting multiplied. Now, let us make this. You require 100 turns, for example. You require 100 turns. So, in each turn, if you have 2 volts, 100 turns, how many volts will have? 200 volts. All are bunched together. All are bunched together. Here you will have 100, here you will have 100 bunched together, placed in one armature. Instead of doing that, if you distribute all these 100 turns on one side, 100 turns on also, total 200 conductors, if you distribute them 20, 20, 20 on 10 slots, then also you are getting the same voltage. Yes or no? If you distribute, you are getting the same voltage. If you bunch them together also, you are getting the same voltage. Few days back in IES, you were asked this question: what is the purpose of armature winding? From the basic definition itself, the purpose you can know right now. Armature winding. Conductors made into turns. Conductors made into turns and multi-turns. Conductors made into turns and multi-turns to become coils. To become coils, which are arranged in series. Which are arranged in series, distributed uniformly throughout the peripheral of the armature core. Throughout the peripheral of the armature core, in order to improve the shape of the waveform. In order to improve the shape of the waveform. Let us think this is one conductor. 1 volt is the voltage induced in one conductor when it is rotating in a machine. If you have 2 conductors in series, what's the total voltage between them? 2 volts. Like that, if you have 100 conductors, what is the voltage? 100. Here 50, here 50. Let us say, what's the voltage? 100 volts. Let us say. Now we want to design a DC machine to get an output of 100 volts. We want to design a DC machine to get an output of 100 volts. So you can simply have one bunch of coil like this. Here you will have 50 conductors. Here you will have 50 conductors. These 50 conductors bunch together, strap them, place. This is the armature. Place in one slot. Is it clear? Similarly, take another bunch, strap them, tie them together. You have a bunch, you place in one more slot. Is the point clear or not? 2 slots are enough now. If you place all the conductors in such a manner, it is concentrated winding. It is concentrated winding. But instead of this, means there are many slots. I am showing only those slots because you are placing them in those two slots only. There are many slots. If you concentrate all the conductors in making two coils, how many slots you require? Only two slots, right? So let us say one thing like this. You placed one here and one here. Let us say like this. This is all bunching together, placed like this. So this is north and this is south. This is one thing. Instead of doing this, all the 100 conductors are arranged in, let us make split into like this, 1, 2, 3, 4, 5 slots. In each coil, let us make 20 conductors. In each coil, let us make 20 conductors. In this 10, this is one multi-turn coil. Means, in this 10 means total 10 turn coil. Let us make 10 turn coil. How many coils? So total 10. Like that, if you make, you connect them in series and you place them uniformly, distribute them. All are connected in series only. If you distribute, if you concentrate, what is the voltage induced in both cases? Same. There is no change in the voltage, but you can think in this way. Let us think like this. When one conductor passes by a north pole, first in this voltage is induced. Voltage is induced. All the 50 turns same. Next, the south pole comes. It will take some time, and actually this is the voltage. So we'll take like this. This is the voltage rectified after the brushes from a 50 turn or 100 turn coil. If you have uniform, this one, there are many turns like this. This will pass by north pole. Not that much of voltage because there are 100 turns in one only, but here how many turns? Only 10. So like 10 volts. This is 10. After some instant of time, the next coil comes and can we say this is the voltage induced? After some time, the next coil comes and can we say this is the voltage induced? So, as the winding is uniformly distributed, what is the total voltage now? If you add them, the total voltage is like this. You understand? This is one bunch of coil side, this is one bunch of coil side. You will have a high ripple content here. But if there is a winding arranged in series, one after the other, then the voltage is having less ripple content. So distributing uniformly the winding is improving the shape of waveform. This is DC. This is DC of 100 volts. This is also DC of 100 volts. But this is pulsating DC containing high ripple content. This is a better DC with less ripple content. So what is armature winding doing now? It is improving the waveform shape. I will again explain you after the pole pitch how that angle comes later. After the pole pitch I will explain. all conductors are concentrated in one coil, 100 volts, 100 volts like that. Instead of that, if you divide and if you distribute entirely one after the other, you will get, and the net voltage, net means total series, they are in series, net voltage waveform is a better DC. We are not interested, we are interested in magnitude, no doubt, but apart from magnitude, this is not at all useful for applications. This DC is not at all useful for commercial applications. So apart from magnitude, waveform is also important. Here IES, you were asked this question. Consider, this is an armature. These are the slots, placed like this. If this is one conductor or a bunch placed, it should be completed through the other coil side. This is one and the other one. So between this and this, there is some conductor. This is extended like this, is a connection. So you can't simply connect like this. It should have a diamond shape, a V shape coming like this. You can't simply cut like this because of high mechanically it's not correct to bend like this. The coils are simply forming like diamond shape like this. So some part is coming out, yes or no? Consider, think about the practical armature winding. If the winding is coming like this, some part is coming out, it will go like this, right? So some part, this is that. So in the machine, from this part to this part, there are poles inside. Some part of winding is coming out, these are connectors at the back end as well as at the front end. So the part which is not cutting the flux, this part is not cutting the flux, only this part will cut the flux. In the first you have written PLV sin theta, across L you have written active length. Active length means the length which cuts flux, only this portion. This is known as the conductor. The length of wire responsible for the induced EMF. The length of wire which is in the magnetic field, which is cutting the magnetic field, is known as conductor. So this is one conductor and this is the another conductor joining at the both ends. This is known as one turn. First keep the subheading conductor. The length of wire. The length of wire lying in the magnetic field. The length of wire lying in the magnetic field. Where EMF is induced. The length of wire lying in the magnetic field where EMF is induced is known as conductor. So you can take AB as one conductor, CD as the other conductor. So you can represent it by Z. Conductors are represented by Z. Let there be Z number of conductors later. Conductors are represented by Z. According to Faraday, they are represented by N actually. Yes or no? E is equal to N d phi by dt. So here we are changing the notation in our the standard notation is conductors are represented by Z. N is taken for speed of rotation, N RPM. So N is represented by Z here. Number of conductors. Next, subheading turn. Two conductors make one turn. Two conductors make one turn. So if there are Z conductors, how many turns you will have? Z by 2. If there are Z conductors, there will be Z by 2 turns. You know, this is one conductor, this is one conductor. So 2 conductors, 1 turn. 4 conductors, 2 turns. 6 conductors, 3 turns. So turns are always conductors by 2. Give the subheading coil. Coil. A coil consists of one or more turns. A coil consists of one or more turns. If there is only one turn in a coil, if there is only one turn in a coil, it is single turn coil. It is single turn coil. In bracket, not used practically. Not used practically. Single turn coil, in bracket, not used practically. Next. Generally, multi-turn coils are used. Which contains 2 or more number of turns. I'll make you to solve a problem at the end containing 18 turns per coil. What will the voltage used in that? Practical machines. So how much this coil is? 4-turn coil, can we say that? Multi-turn coil, what is the voltage output? 8 volts. Now, this is one coil. This is called as one coil now. A coil has 2 coil sides. Right now, a coil has 2 coil sides. Which are placed in the slots. Which are placed in the slots with a coil span, which are placed in the slots with a coil span. Now I am representing this only. All these are bunched together. All these are bunched together. This is that. This is the coil side. So practically there are no 4 turns, there are many turns. I am representing like this. So these are bunched together, strapped together. This is one coil side. coil side. This is one coil side. Now, this coil side is placed in one slot, and the next coil side of a coil will be placed in the other slot. The distance between these two, between this slot and this coil side, is known as coil span. Now comes the important part. Keep this updating pole pitch. Pole pitch. Right on. According to the definition, it is the peripheral distance between two adjacent poles. Right on. Peripheral distance between two adjacent poles. Listen now. Another way you can take like this. There are two poles. The entire armature, the slots on the armature or the conductors are rotating at any one instant, If there are two poles, half of the armature comes under one pole, half of the armature goes under the other pole, right? If there are four poles, then 1/4 of the armature part comes under the one pole, and 1/4 part goes under the other pole, 1/4 part. So finally, the poles are spanning the armature completely actually. So each pole, how much it is spanning, right? So for example, if you take like this, a 2-pole machine, if there are S number of slots, for example 10 slots are there, what is pole pitch means? Can we say 10 by 2? 10 by 2 number of slots per pole, or number of conductors per pole, anything, but finally what you are doing, you are dividing the total by each per pole basis. What is this pole pitch giving you an idea? This is the basis for the machine design, winding design, in AC machines or DC machines. What is the pole pitch telling you means? We are placing one coil side of a coil in one slot randomly. That is the first slot. When you place one coil side of a coil in one slot, the pole pitch gives you information at which distance should be the next coil side of that coil should be placed. Means, will you place here or here or here or here? Where you have to place, pole pitch will tell you correctly. According to the information you got from the pole pitch, if you place, then you can have maximum induced EMF. Then you have maximum induced EMF. What does this mean? For example, let us say this is the coil side. I am representing this as one bunch strap. This bunch is represented like this. This is one bunch represented like this. Now, if you place the coil side here, and if you place the coil side here, let us say like this. In this, the coils are placed on the armature. What is the voltage induced in this coil? At any instant I am taking. At one instant, at this instant, what is the voltage induced in the coil? Let us say here maximum. You know, positions 3 and 7, you have maximum induced EMF. Position 1 and 5 have 0. Remember that? So this is position 1 and 5, and this is position 3 and 7. If you place here and here, for example, what will be the voltage? This is maximum, this is minimum, 0. Right? So let it be 1 volt, this is 0. So what is the total voltage? 1. If you place coil side here, and if you place, instead of this, if you place here, you will get maximum plus maximum. So how much you will get? 2 volts. For example, if you have 12 slots, if you have 12 slots, each marking one slot, and if you have 2 poles now, let us say this is 1. So you are starting with 1, let us say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For your easy understanding, I am giving numbering to you. Let us take, there are 12 slots in the armature. It is a 2-pole armature. What is pole pitch according to definition? Can we say 6? Pole pitch is nothing but 6, because 12 by 2 is 6. Now this is the pole pitch. What is this number 6 is telling you means? If you place the first coil side in the first slot, and if you place the coil side of that coil in the 7th slot, you maintain 6 coil span. Maintain the coil span as 6. Means 1 plus 6 is equal to 7. You maintain in between 6 exactly. So place the coil sides in 1 and 7, or 2 and 9, or anything, but maintain how much? Exactly pole pitch width. If you maintain, then what is produced in that coil? Maximum induced EMF. Through which factor you are getting this information from? From pole pitch. For example, if this is a machine given to you, it has 2 poles, 12 slots. Then you will calculate pole pitch for this machine. Pole pitch is nothing but 6. 6 means if the coil span of a coil is exactly equal to pole pitch. What is coil span? Distance between 2 coil sides of a coil is exactly equal to pole pitch. Means these are the slots, these are the poles. Under that, if you place them exactly, what is the distance between 2 adjacent poles? Pole pitch, right? So if the coil span is exactly equal to pole pitch, then maximum induced EMF, that coils are called as full pitched coils, and the winding is known as full pitched winding. Well, pole pitch can be expressed I am representing this diagram in easy way, in a horizontal way. Just imagine. North pole, north pole. This is stator, south pole, stator part. And you know these are all the armature slots. Just represent like this. If first slot comes under the north pole, automatically seventh slot coming under south pole. That's what I have represented. So now this coil. You want to design this coil. Now bring this coil, this bunch. One coil side of the coil is placed in the first slot. The next coil side of the coil should be exactly placed in the seventh slot, which means you are making 6 slots as coil span. Between 1 and 7, how many slots are there? 6 slots are there. Coil span. To the subheading coil span. Let coil span. Distance between. Write down the definition for coil span. Distance between two coil sides of a coil. Distance between two coil sides of a coil. Next point. If the coil span is exactly equal to pole pitch, if the coil span is exactly equal to the pole pitch, it is full pitched coil. It is full pitched coil. Where maximum EMF is induced. Where maximum EMF is induced within the coil. Maximum EMF is induced within the coil. DC armature windings are. DC armature windings are full pitched winding only. DC armature windings are full pitched windings only. So we are not deviating. There are short pitch coils to reduce harmonics, everything that will be discussed in AC windings. But in DC windings, particularly the windings are only full pitched in nature. Now listen. One simple basic here is the distance between this pole to this pole is known as pole pitch, no doubt in that. Let us consider one conductor is making from this point to this point, means under the North Pole you have one cycle. The same conductor, when it comes under the South Pole, you will have another cycle. One electrical cycle is 360 electrical degrees. One electrical cycle is known as 360 electrical degrees. One mechanical rotation from this point to this point, one mechanical rotation is also 360 mechanical degrees. Is also 360 mechanical degrees. Here you have to know clearly what are mechanical degrees, what are electrical degrees. You have to know the relation between them. Now, if there are two poles in a machine, one mechanical rotation of 360 degrees mechanical produce 360 degrees electrical. Sorry. Just consider one complete mechanical rotation of 360 degrees mechanical. In this rotation, you will have a positive, you will have a negative cycle. One positive cycle always 180 degrees, one negative cycle always 180. One cycle electrical means automatically 360 electrical degrees. So, if there are two poles, one complete rotation of 360 mechanical is equal to 360 degrees electrical, since two poles. Now, let us think. There are four poles now. Same 360 degrees mechanical rotation. When a conductor make 360 degrees mechanical rotation, you will have under one north pole you will have one cycle, under south pole you will have one cycle. This is known as one electrical cycle. This is known as another electrical cycle. Always one electrical cycle is 360 electrical degrees. This is known as another 360 electrical degrees. One rotation is 360 mechanical degrees. One cycle 360 mechanical degrees. Similarly, always one electrical cycle is 360 electrical degrees. That's it. So this is 360, this is 360. So total how many electrical degrees? 720 electrical degrees. Why? Since how many poles? 4 poles. If you extend this, if there are 6 poles in a machine, one complete mechanical rotation of 360 degrees mechanical will produce how many cycles again? 1, 2, 3. So total 1080 you will get 360, 360, 360. Total 1080 electrical degrees. Because how many poles? 6 poles. Now what is the relation between electrical and mechanical degrees? It depends on number of pairs of poles. Can we say that? Electrical and mechanical degrees are deviating because depending on the number of pairs of poles. If there is one pair of pole, mechanical degree is equal to electrical degrees. If there are 2 pairs of poles, mechanical degrees became 2 times. If there are 3 pairs of poles, it became 3 times. But one thing you will observe in common, under a pole, always there are 180 electrical degrees. Observe this. Under a pole, it may be north pole, it may be south pole. Let the machine contain 2 poles, let the machine contain 1000 poles. Irrespective of the number, always under a pole there are 180 electrical degrees. Yes or no? Why I am discussing all these things means pole pitch means 180 electrical degrees. What is a pole pitch? It is the peripheral distance between 2 adjacent poles. 2 adjacent poles. Let the machine contain any number. For example, from this point to this point is 1 pole pitch. This point to this point is 1 pole pitch. Or if you separate from this point to this point, this is 1 pole pitch, this is the other pole pitch. So for 2 pole machine, this is the pole pitch. For 4 pole machine, from this point to this point is 1 pole pitch, right? Distance, peripheral distance between 2 adjacent poles. Between this north and south, 1 pole pitch. This south and north, 1 pole pitch. This is 1. So the total armature divided by 4. So even though if there are 6 poles from this point to this point, mechanical degrees are varying, but always under a pole, under north pole you will get 1 cycle, half cycle. Under south pole you will get 1 half cycle. If there are 4 poles, you will get 4 half cycles. If there are 6 poles, you will get 6 half cycles. So 1 pole is responsible for 1 half cycle. So 1 half cycle means electrically it is 180 degrees electrical. So 1 pole pitch is always 180 degrees electrical. Make a note. So first, what is the relation between this electrical and mechanical degrees? You can write like this: theta m mechanical degrees is equal to theta e by p by 2. Can we say that? So apply this formula to the first case. Theta m is equal to theta e. How many poles are there? 2 poles, 2 by 2, 1. Apply to the second case. 360 mechanical degrees. How many electrical degrees? 720. Apply. In place of theta e, place 720. So theta m 360 already. So theta e 725. How many poles? 4. 4 by 2. 2. So 720 by 2 equal. Like that, if you place here 6 poles, 6 by 2, 3. How many theta electrical degrees? 1080 by 3, you will get 360. So finally, what you can say is theta E is equal to theta M into P by 2. You need this formula particularly while calculating demagnetizing ampere turns per pole, cross magnetizing ampere turns per pole in armature reaction topic. I'll make you understand clearly regarding that. In electrical machines, we are interested in electrical degrees but not mechanical degrees. Remember this simply. In electrical machines, we are interested in electrical degrees but not mechanical degrees. Throughout electrical machines, only one machine, that is stepper motor, we are interested in mechanical degrees because the rotor makes angular steps in mechanical degrees. Only that case. Total electrical machines, always we consider electrical degrees. Next. Make a note now. There are always 180 electrical degrees. There are always 180 electrical degrees under a pole. Under a pole. Therefore, under one pole. Therefore, one pole pitch is 180 degrees electrical. You have to say electrical, otherwise it will be wrong. Because here, what is the pole pitch? If you say 180 degrees, mechanically 180, but what is the pole pitch here? It is varying, right? So always 180. If you say this point to this point, 180 electrical degrees. From this point to this point, how many electrical degrees? 180. From this point to this point, how many electrical degrees? 180. Let it be 1000 poles. Let it be 1 degree mechanical, but you will get 180 degrees electrical, always under a pole.
बता दे यार, मैं एकला बैठा हूँ दादा को मैंने बता दो, मैं भी आस बाकी इनको जापा था जी ना खींच के ले रहे हुए सारे साउथ के लोग बढ़िया पढ़ा है भाई। अरे कितना टाइम है? 12:45।
Single layer winding. The heading single layer winding. If there is one coil side in one slot, it is single layer winding. Double layer winding. if there are two or more conductors, coil sides, if there are two or more coil sides, if there are two or more coil sides in one slot, arranged in two layers, arranged in two layers. You can observe two layers means this is one layer, outer one, this is inner one. Clearly differentiated 1, 2, 3, 4, odd number, even number. So two layers. It is double layer winding. Arranged in two layers, it is double layer winding. So two or more means you can have 4, you can have 6 also. But two layers are common. Here also you can observe the same structure. Outer layer odd number, inner layer even number. To make you understand this data, there are 30 coils, 60 coil sides. If you do single layer winding, how many slot armature you require? 60 slots, because each coil side is placed in one slot, so you require 60 slot armature. If you go for double layer winding, this is the standard double layer winding. If you are not given anything in the problem, simply you are given double layer winding. Then you have to take two conductors in one slot, two coil sides in one slot, another standard double layer. So in this, how many slot armature you require? 30 slot armature is required. So here, how many slot armature required? Only 15? Right? So like that, what you are reducing the armature? Periphery. If you have large number of slots, 60 slot armature, large diameter, 30 slot armature, small diameters. So finally, you are utilizing the slot area effectively and you are making the machine to become compact. So generally, double layer windings are preferred than single layer windings. Single layer windings is only for small machines, but generally preferred is double layer. This is all about sharing a room. If you have one room, in that one room, two persons can share, or single person can stay in that room. That is about this. The next one is multiplex windings. That is totally different. Keep the heading. Multiplex windings. Listen, DC windings are closed windings. Let's listen. DC windings are closed windings. Means if you start the first conductor, you will connect all the conductors. Let us say there are 12 conductors. you will connect all the conductors and finally you will come back to the first conductor. That is what is known as closed winding. If you start with the first coil side or coil something, you will connect all the coil sides and you will come back to the one. Means it is completely closed winding. Now, in this closed set of winding, if you have all conductors, they can be arranged in single layer or double layer depending on the slots in the armature. Any type you can go for that, right? Now, multiplex windings means you will have two or more independent sets of windings. This is only one set of winding. Only one. All the 12 conductors making one set of winding. Instead of that, 6 conductors. You will start with first conductor. You will connect all the 6 conductors and you will come back to the first conductor. This is all the 6 conductors make one set. Again, some missing conductors will be 2, 4, 6, 8, 10, 12. This is 1, 3, 5, 7, 9, 11. 2, 4, 6, 8, 10, 11. These things, let these 6 conductors make one more set. So how many sets are there now? 2 independent closed sets of windings. If you connect them in series, both are same. If you connect them in series, all the 12 conductors are in series, right? So same format you are getting. If you connect them in parallel, then comes the difference. If you connect them in parallel, then if you say this is one conductor, this is one conductor, this is one conductor, this is one. Each conductor, due to cutting of flux, let us say 1 volt is induced. Each conductor, due to cutting of flux, 1 volt is induced. What is the total output voltage of this particular circuit? I am taking an equivalent circuit for the winding, just for understanding. 4 volts. Next, let us say each conductor current carrying capacity. Morning I have told you 2 things. There are 2 electrical design constraints. One I have told you regarding insulation, and the next one is coming down. The thickness of the conductor means cross-sectional area of the conductor depends on current carrying capacity. 2 electrical design constraints. One is the voltage, operating voltage of the system. It may be a meter, it may be a transmission line, it may be a machine, anything, a cable. The insulation level in that depends on the operating voltage. That is one. Similar to that, the thickness of the conductor or the cross-sectional area of the conductor depends on its current carrying capacity, current rating. If you go to your machine lab, if you take a 5 amperes fuse wire, thin wire it will be. If you take 20 amperes fuse wire, the fuse wire thickness increases, so on, like that. So the thickness of the conductor depends on its current carrying capacity. Now, let us consider winding is nothing but starting like a fuse wire. Winding, what's the definition I have written for winding? Winding is nothing but conductors made into turns. Turns made into coils. Coils made into, all are in series. Means what is the current flowing in a turn and what is the current flowing in a conductor? Same. Is the point clear? Don't think armature current means coming into the load. Yes, you are right. It is the current flowing to the load, but the current is flowing through each conductor. Exactly to say, if you say IA is the armature current outside the armature, inside the conductor, the current is IA by A. If there are 2 parallel paths, for example, if there are 2 parallel paths, if you say this is the current IA, what is the current here in this and in this? IA by 2? IA by 2. If there are a number of parallel paths, what is the current rating? IA by A. So, each conductor should withstand one particular amount of current. Let us say, each conductor here, this thin conductor can withstand 1 ampere. Can withstand 1 ampere only. only. More than that, if it flows, automatically temperature rise comes and the wire will melt away. So the maximum rating is 1 ampere. Similarly, in this part also, how many amperes it can bear now? Only 1 ampere. If you have two parallel paths in the armature, let us say, how parallel paths are forming, we'll discuss. If there are two parallel paths in the armature, if each path can bear 1 ampere, how much current rating will this winding have? 2 amperes. Means, for example, you can say like this. By connecting one bulb consumes 1 ampere. So how many bulbs you can connect now? 2 bulbs. So 2 bulbs are consuming 2 amperes. Now I am making this a circuit like this. Each path contains only 2 conductors. I am making 4 parallel paths. Is the question clear? Now, you think like this. This circuit is made like this. Each path contains only 2 conductors. Now, how many conductors you have? 4 conductors, 4 conductors. Now, let us design like this. Let us think about this. To understand what is multiplex concept, you think like this. Let us say, each path containing 2 conductors only. Each path containing 2 conductors only. So how many conductors have total? 1, 2, 3, 4, 5, 6, 7, 8 conductors. All the 8 conductors are arranged in how many paths? 4 parallel paths. By cutting of flux, each conductor can produce how much volt? 1 volt, 1 volt, 1 volt, 1 volt. So what is the total output? 2 volts. Each path can bear how many amperes? 1 ampere, right? Common, that's the common thing. This conductor can bear 1 ampere here or here. It can bear only 1 ampere. So what is the current rating now? It can bear up to 4 amperes. Can we say that? Now, due to increase in the parallel paths, what happened? Current rating increased. Load capability increased. So, come back now. These windings are connected in parallel. In order to increase current rating, loading capability. I'll extend this after lap and wave again. I will connect these two waves because in wave it is advantageous than lap. There is a reason for that, then you will understand. First, write on this. Multiplex windings. DC windings are completely closed set of windings. Completely closed set of windings. If there is only one set, it is simplex winding. It is simplex winding where multiplicity factor M is equal to 1. Multiplicity factor M is equal to 1. If there are two such independent closed sets, of windings on the same armature, it is duplex. Multiplicity factor m is equal to 2. Similarly, 3 sets m is equal to 3 triplex winding. Similarly, 4 sets quadruplex. So take an example. For example, if there are 12 conductors, there is only one set. In all the winding, all 12 conductors are there in series. Duplex, 6 conductors form one set, 6 conductors form the other set. Both are arranged in parallel. Triplex, 12 conductors total, divided into 3, 3, 3, like that, 4, 4, 4 into 3 sets. So if you arrange them in 3 parallel paths like that. So what is happening in the machine? Is the current rating increased or not? Here you can connect 2 bulbs. Here you can connect how many bulbs? 4 bulbs. But you will observe one thing. With the same number of conductors, if you are asked like this in the question, for the same given number of conductors, multiplexity increases current rating but reduces voltage rating, because as you increase the number of parallel paths, conductors per parallel path are reducing. Observe, if there are only 2 paths, 4 volts. If there are 4 parallel paths, only 2 conductors per parallel path, so only you got 2 volts. So if there are more number of conductors in series, more voltage. If there are more parallel paths, you will have more current rating. Right now, multiplex windings increases the current rating, and the loading capability of the machine. For given number of conductors, next point, for the given number of conductors, multiplex windings increase. Current rating while decreasing voltage rating. Change the color of the pen, make a note. These are more advantageous. In wave winding. These are more advantageous in wave winding than lap. See the board. Wave winding than lap winding. You understand why they are advantageous. Later we'll discuss about lap and wave. Now listen, what is the difference between multiplex winding and double layer winding? This is the general confusion. After some days, if you read any, the general confusion is, what is the difference between multiplex windings and double layer winding? Multiplex winding can be single layer, can be double layer. Yes or no? Let it contain 2 sets or 4 sets or any number. If you have more number of slots, you can go for single layer. If you have less number of slots, you can go for double layer. So multiplex windings can be any layer, but double layer winding cannot be multiplex. Double layer, single layer is all about things like sharing a slot. If one slot, one coil side, single layer. One slot, 2 or more, it is double layer. Multiplex windings can be arranged in single layer winding or double layer winding. It is all about independent sets of windings which can be arranged in parallel. So after discussing lap and wave, I will make you to understand more clearly with the diagram regarding multiplex windings. So if you have winding is nothing but connecting the conductors in series at the back end, at the front end. Can we say that? You have conductors, let it be some 20 or 30 conductors. If you want a winding is all about connecting these conductors in series at the back end and at the front end. Simply like that. At the back end, at the front end. At the back end, at the front end. If you connect, automatically you got a winding which is connected in series. So how to recognize the back end, how to define back end and front end? So there is a fixed format. If you have a DC machine, the end where commutator is connected is known as front end, and the other end is known as back end. There's a reason for that. Right on. Keep the sum feeding. Front end. The end where commutator. The end where commutator is connected. The end where commutator is connected. Back end. The other end of commutator. The other end of commutator. Front pitch. Front pitch. See the subheading, front pitch. Number of conductors. Number of conductors. Spanned by. Number of conductors spanned by one coil. Spanned by one coil at the front end of the armature. Spanned by one coil at the front end of the commutator. Sorry, armature. Next, back pitch. Back pitch. Number of conductors spanned by one coil at the back end. At the back end of the armature. Now listen. Let us consider 1, 2, 3, 4, 5, 6. This is the back end of the machine. This is the front end of the machine where commutator is connected. If you want to connect first conductor to any other conductor, you require one value, that is back pitch value. For example, if back pitch value is 4, then you are connecting 1 to 5. Is that clear? Similarly, if 5 is coming back and connected to 2 means the front pitch value, this is the front pitch. The front pitch value is 5 minus 2, that is 3. If you want to do winding, all you require is these two things only. If you want to design winding, all you require to do the winding is you have to know back pitch value and you have to know front pitch value. Once you know these values, the winding can be successfully done simply. Tomorrow I will tell you how to simply calculate these things and draw the winding diagram. All you require is back pitch value, front pitch value. If you know this, simply you can connect all the conductors and you can do everything. So these are the definitions. You will understand the meaning of the definitions in the diagram tomorrow. Next, commutator pitch. Keep the heading, commutator pitch. Number of commutator segments. Number of commutator segments. Between two successive coils. Number of commutator segments between two successive coils. Resultant pitch. Distance between the starting of first coil and its next successive coil. Starting of first coil and its next successive coil. All these four I will represent in a diagram and explain to you tomorrow. Listen, 5 minutes more. Okay, and you.